That's an error. So this is one of the ways where we make functional programming easy by making it zero cost. It's a one-letter change to say your data is now immutable. And this works not for just primitives, of which this is not actually, oddly enough, and we will get into that in just a second, but also class types, in that you know once something is constructed and it's a val, that's final. That's what that thing points to for the rest of its existence. In terms of primitives, so this is something that I find amusing. Scala is both more OO than Java and more functional. So what do I mean that Scala is more object-oriented than its mother language, Java? B is actually an object as far as the developer and the compiler is concerned. It is an optimization detail that something like int would be turned into a primitive type. Let that sink in. That's something that the compiler should worry about, right? Because in any sane language, you shouldn't have to care. And Scala goes out of its way to make sure that that is the case. So that when you're looking at an int, you really don't care, because I can do this. Good luck writing that in Java on an int. Now you can do it on integer, which is a boxed class of that primitive. But if you have the primitive, integer, you can't do that. There are no methods on my object. So this is one of those things where Scala says, yeah, let's actually treat things as the objects they are, which I think is remarkable. And that's, it's a really nice combination. Okay, so we can do some basic math, but I hope this gives everybody the flavor of what's going on. Now, note that we used a var here where this is. So what happens if we say a equals 9? What happens if we do 7 again? Well, that computation has already been done. So at the time that that computation has taken place, that var is evaluated, and we know what it points to, and we do our math, and that's what it's going to point to forever. So it doesn't matter if we go and change a, hey, we're done, which is good. We actually get access to more than just ints and floats and things like that. We get access to things like this, tuples. Having nice tuple primitives is really, really handy. And Scala goes out of its way to put uniformity into its syntax. It's actually one of the most consistent languages that I've ever run across. So for example, if we wanted to declare a list, which is not an array, by the way, it really is a linked list, we do something like that, which looks both clean, but it's also immutable, which is really cool. So all of the standard collections that Scala gives you, you have to go out of your way to make mutable, to get mutable versions of. In fact, sometimes they'll be named something different, in that you'll go looking for like a mutable hash map, and it'll be named like, I think actually mutable hash map or something like that, mutable map. It sort of hides these things and it very much encourages the use of immutable data structures. Now, again, these are immutable by convention. I could pass this down into Java, and Java could screw with that data structure all day long. And actually, it wouldn't even necessarily have to do bad things using, say, reflection. We saw this in the decompiler, where with traits, which are an OO primitive in Scala, there are just methods that you can throw random data into and completely destroy your Scala objects. Now, if you ever see somebody doing that, that's a very, very bad sign, but it's possible. And there's no way to stop them. That's other than a linter picking it up. So we get access to, easy access to lists. We get maps. We get nice map primitives. Let's do string. And can everybody see that? Like,
A tiny bit small.
I wonder if there's a way to, let's see if we can put this up, because I get the feeling that anything down below is going to be really hard to see.
Change the contrast? Like flip the colors of black on black?
Yeah, that's a good point. Let's do that. Anybody remember where that is in iTerm? I haven't changed that in years.
It's under profile.
Is it under profiles?
Wasn't it the theme, light and dark?
There it is right
No, but if you change
Can
the
I
theme, it
do-
will do all the colors automatically, right?
New tab with current profile. New tab. I'm sorry, I don't want to change it because I actually have. No. Okay. Well. Okay.
Just make a new profile, call it like high contrast. And you can just right click on the terminal window you're on and change your profile without having to do anything.
Play background. Here we go. No, don't set us.
So after you save it, just exit and then right click on the terminal window. And then there's like a profile button. Or like inside of the...
Not inside, yeah.
All right. Yes. Okay, so we saw all of those interesting things. We have map. Which uses a little bit of an odd syntax, but what's cool is that everything used here is stuff that's exported through libraries rather than built into the language. So most languages that support maps do so via some kind of like parsing primitive. They actually define a grammar for expressing a map. Scala, on the other hand, for better or worse, has more or less free-form operator overloading. And it sort of has a consistent way of viewing method calls on objects. So if everything is a method, then an operator, or if everything is an object, then operators are really just methods on those objects that take arguments. And that's actually how Scala views this code. In that arrow here, it's actually the name of a method. You can't really write that name in Java, but you can on the JVM and you can in Scala. And so this is where, because we can target things at a slightly lower level, and we don't always have to be 100% compatible with Java, we can get away with defining helpers like this. So like, what would this return? Well, it turns out that arrow, with the object that it has and the object that it points to, just returns a tuple. So let's define this map. And we had a tuple before. Okay, well, what if we do that? Hey, it's just another tuple. So the map constructor now just takes a list of tuples, which is a really, really elegant way of getting around the problem of not having map literals, or a literal really of any kind, in your language. You can do all of the fancy syntax that looks really, really pretty and parses correctly, but entirely as a library. I think this is one of the ways that Scala is really neat, because now it's all just immutable. I now have a mutable map that I can do things with and to. So if I want to do this, the option, or the result type here of getting that key is one of the other interesting things about Scala, in that just because we have to deal with null doesn't mean we have to like it. So, so for example, one of the things that we do is we have an option type, the option monad. It really is a monad. And it's an algebraic data type with really 2 inhabitants. Now, viewed from the type system, this gets really fun, but it's the same as Haskell's maybe. So you have just something and none, I think, are the 2 inhabitants of that. Here we have some type, and we have none to indicate the absence of a type, or the absence of a value. So here we did a get of A, and that key exists in the map, so we return a sum of 1. We don't return null. Instead, if we try and get something that doesn't exist, we just get none. And so now we're forced into checking in our code whether or not the thing that we tried to grab at runtime actually exists in the map that we're looking at. Now, we have ways in Scala of saying that maps must actually contain something, because we can do type system trickery and hackery. But most coders aren't going to write that, and that's a compile time thing, which is only ever going to look at literals. So we now have a type-safe, sound way, in as far as Scala can be safe and sound, of looking at values in maps. And the option monad is used all over the bloody place within Scala. Maybe too much, maybe too little, but it's definitely there, it definitely gets used. And we have other similar things like either. Is it dot right?
You just use the word right.
Oh, that's right.
Yep, there you go. Yep.
So like the 2 inhabitants of either are left and right. You instantiate them using, well, left or right. So we can have left of 1. And the type there, we can go into how the Scala type system lies to you in a lot of ways.
Yeah, you mentioned val colon. You gotta put your variable in.
Oh, yeah, need a name. There we go. So that's now an either. And we could definitely have there we go. And now if I actually want to inspect the value of x, and by the way, the reason that I can do this is because I'm on the REPL. In regular code, you couldn't actually do that. But if I want to pull out the actual value of x, I now either need to do a type assertion on it or pattern match. So I know my code is safe when I'm pulling these things apart. So we've looked at var, val, map in some of the collections. Let's look at how we define a function real quick.
So what was the value of x in that case? You assigned two values to the same?
So the type of x is either int or string. Its value is right of literal a.
Did you mean the 2 x's? Like he should have probably used y in the second
Oh, yeah,
case.
yeah.
There's an artifact of the thing he's in. He could actually say there's
So
a
here's x.
scope that continues to expand with each line, and so that's how he's doing. There you go.
Yeah.
Quick, map a function over it.
So this is where most of the, well, so you can't map over an either because it's not a monad. It's not right biased.
It's
So
not a functor? It should be a functor.
there is a functor in Scala Z for it, I
Oh.
think, but I think you're forced into using validation, so which is a different one. Yeah, either doesn't get very much love. There's like 17 replacements for either. So
There is a Scala Z import you can use that gives it the proper bifunctor and monad interfaces.
And his right bias.
Yeah. But typically, if you're going to be using Scala Z, you'll use one of their implementations of either.
yeah.
So what, the default one, it's not that great.
It just has a lot of baggage with it, I guess, because no one seems to like it. I can't explain.
Well, it was the original, and they're stuck on the. You get enough code written. The original either, I mean, the either that comes in the Scala util, I think is where it is. that was originally written in Scala 1.0 or 1.1.
Yeah, it's really old code.
And so, the early Scala was essentially a handcrafted compiler. And so the implementations of the initial implementations and stuff are all handcrafted. So they're relatively fragile. As they've matured though, of course, the core ones got too much use and now they're stuck with either in the library. They can't change it, there's too much code that depends on that particular semantic. So that's why all the variations have sprung out.
So the question would be, whatsoever the replacement for the default? Do you have a recommendation?
So Odersky has been waiting for an opportunity to shove Scala Z actually into Scala. So what happened, Scala came out, and then the FP guys went, okay, this is an abhorrent mess. We're going to make our own thing. And there's one guy, Tony Morris, who basically led the charge and created Scala Z. Odersky saw Scala Z and Scala Z and said, this is awesome. We really need this in the core. And of course now they've got this catch-22 cycle. There's already code written on it. And so I would say that most people who are interested in doing serious functional programming in Scala use Scala Z.
Or cats.
Well, yeah, that's actually more recent, but yeah, cats. Yep.
But with Scala Z, they introduced something called a disjunction, which is the direct replacement for E, which has a monad instance. And then there's also validation, which could be used as a monad, but they keep it at the level of applicative so that you can get the fail slow semantics.
Yeah.
Earlier, your left and right, they showed up in the REPL with types of like left int nothing and then right nothing string.
Well, no, it's actually type inference, but
Yeah, so default it's in nothing for the other.
Yeah.
Yeah, that's what I'm thinking, but why does that exist?
it's, well, so I mean, you've got two obvious ways of type inference going, right? So let's type that in and see. It could be any, or it could be nothing. The Scala compiler is pessimistic. So you can have nothing in the Scala universe is the bottom type. You can have no subtypes of nothing because nothing is a subtype of everything. And so this says because you haven't specified, go to the bottom type, which is the safest, soundest thing to do.
Can you write left where you specified the right type? Yeah, exactly. Now that forced the type by causing it to instantiate it.
So now, rather than going through type inference, we've actually specified what the types are.
Exactly.
And the nothing thing works because it's covariant, and so you can cast it into another type state. Essentially.
Yeah, either is
I
covariant.
guess my question was that just sort of a hack to get the same left-right sorts of behavior? Like, so you just don't have to worry about what's in the nothing place, you know?
So
So you just pattern match on the int and you just ignore the nothing?
Yeah, that's mostly what you would do. And
Well,
so Jacob's right. The thing is going to help you out because the way that either is defined, left of int and any is a supertype of left of int and nothing.
Right.
Okay.
Ultimately, though, you're rarely going to write a left. I mean, very rare. So for my code, when I'm writing, it's going to have a right pathway and a left pathway. The type inference is going to surface both of the types to the top. Does that make sense? So it's very. I mean, this nothing instance is extraneous technically. I mean, for my implementation, I don't ever use nothing.
Okay. Well, you can't write nothing. I mean, it's
Oh,
actually
yeah,
impossible.
right. Yes.
So, but yeah, this is sort of where the interesting interplay between a language with subtyping and a language that I'm not even sure. Does Haskell have subtypes? I don't think it does.
No, it doesn't.
Right. So, like, what hacks do you have to do to make this stuff work in a language with subtyping? Because we actually have to worry about polymorphism and inheritance over here. So now all of a sudden we really want, list of int to be a subtype of list of any. I mean, that's code that I want to be able to write. Well, we need ways of doing that, and so the Scala type system is really powerful. It actually defines at the top an any type, which is different than Java's object type. It really is, because it encompasses both what are called vals, which are the supertype of all of the primitives on the JVM, as well as any ref, which is any object type over there. So they went ahead of the JVM in a lot of ways of trying to categorize and rationalize the fact that Java actually has two different kinds of things that it's thinking about, and it's not thinking about them in a safe way. Scala did the best it could, and so you've got at the top that nice hierarchy, and then they went one step further and actually introduced a bottom type, so that now you can do things like that, and it's sound, so, as well as contravariance and covariance annotations and stuff.
Well,
like
you get
that.
an a directed acyclic graph with a terminus,
Yeah.
which is it actually makes reasoning in the compiler actually very elegant and nice.
Yeah, you actually know who your
Yeah.
supertypes are.
Bertrand Meyer, Eiffel, he was the one that was introduced in Eiffel. And he basically said this allows me to terminate the reasoning.
Yeah,
So,
which makes sense.
yep.
Okay, so let's look at printing some output. Yay, this will print hello world in the console. That's not very exciting. Let's look at defining a let's look at defining a function first. So A is going to be a function from unit to, I don't know, int. Let's apply. Okay, so A is now a function that takes no arguments and returns an integer. In this case, I mean, it could return any integer, but in this case, it's always just going to return 1 because of how we've defined it. To evaluate our function, we use parentheses, and so A just passed back is that data, that function. But if we evaluate A using the parentheses, now we get our 1 back out. Okay, so we actually have a fairly concise way of both declaring functions, binding them, and evaluating them. This is something that Java programmers have always wanted. They now finally have it as part of Java 8. We've had this for a long time, and it looks really, really nice as far as I'm concerned. So let's do something more fun and declare this. What?
Lazy val.
Oh, I forget those things.
Mm-hmm.
Okay. So now we've evaluated it. Our block includes a side effect, which you can do in Scala, but it's lazy so that it wasn't actually instantiated on this first line where we wrote it. Because remember, all of the other lazies that we did, or all of the other vowels that we did, immediately instantiated themselves and did output there. Here, we actually have a keyword-based way of saying, wait, don't actually do anything until we actually need the value. And so then on the next line, we can evaluate B. It's not a function, it's just regular data. Goes off, evaluates it. It memoizes that value, so if you call this lazy again, or if you call B again, the return will be very, very fast. It uses a bit mask underneath, and it's very nicely optimized. But I'm pretty sure, yep. There you go. So the side effect gets evaluated once. Woo, fun. So that means you can do interesting side effects once as part of a lazy. That sometimes gets used, I'm sure. All right.
If you have a function that inserts something in a database and then immediately returns it to you, and you're using that multiple places inside something else, then your insertion into the database can only happen once.
Yep.
It's useful.
But what happens if it fails?
Everything else fails.
Well, hopefully.
Yeah.
Let's see.
Not a recommended strategy. Yeah.
Yep.
minus equals.
There we go. So one of the control flow mechanisms that we have access to in Scala is while. And while works exactly the way that you think it would. In order to make really good use of it, you're probably going to write it in the Java style, in which case you're going to have a var off someplace as an index, and you're going to either be incrementing it or decrementing it. Hopefully you won't be writing code that looks like this. Hopefully you'll probably be incrementing from 0 on and doing stuff like that. But this really does make Java programmers feel at home because the syntax looks and feels exactly like Java. But it's very much an imperative programming construct. Now, Scala has a for loop, but it is nothing like the for loop of Java. It doesn't feel the same, it doesn't work the same, it doesn't do anything the same as what Java does. The biggest similarity, and I think a large downfall, is that it calls itself for.
Yeah.
When it would actually make more sense to call itself do, because the for loop in Scala is actually do notation from Haskell. I think is really, really neat. So let's look at some of them. Is it range?
Yeah, range. You're trying to do a range. Yeah, 1 to 10.
Yeah, I think it's that, right?
I think you just do 1 space TO space 10, and you don't even have to type range. It knows that as the import.
Is it 1 to 10? Is that what it is?
1 space TO space 10, I believe.
There we go. So again, 2 is the helper method. We get all kinds of interesting things in Scala. That does not work the way that you would think it would. And it also doesn't work the way that a Java for each iterator does. Now, it turns out that this actually is going to use the for each method. The issue is that we can do something like this. And all of a sudden, we've done a for comprehension. So we don't necessarily have to do anything side effecty in the body of the for loop. We can just run through whatever generators we have up here, effectively, and then yield some computation down at the end, which is really, really cool. Oh, are we out of chairs?
Yeah.
I guess we are. So what's nice is that this syntax is actually desugared into flat maps, into basically a giant monad that carries itself through. And so if you want to read this in sort of a Haskell mindset, replace for with do and yield with return, and the syntax is almost exactly identical. And the operation is very, very similar. So what's nice is because it's aware of monads, you can actually imitate almost all of do notation in here. In that, for example, if you wanted to do stuff with the free monad, in that you want to put together declarations of program code, declarations of intent, you can do that, chain them together using what is effectively the semicolon monad, and now that's code that you can go evaluate later on, but it looks like imperative code because of how you've written it. In that you know that the first thing will occur and then the second thing will occur, and so it's actually really, really neat. We have access to that really powerful construct. Let's close that one. We've looked at lambdas for each flat map. So this is really going to be the functional programming primitive that most people use. And it's because our collections support map. I mean, that's probably the biggest benefit and the thing that is most leveraged in Scala code that really has its roots in functional programming, in the world of functional programming. It really is the fact that you can map or flat map, do these very generic operations across collections, and we have easy, concise access to it. So if I declare a list of 1, 2, 3, 4, and I add 2 to each of those elements, I now get a new list of 3, 4, 5, 6. And what's really nice is it's as simple as that. Because Scala, like, if you were to write this code in Java, it's going to end up being, what, 10, 15 lines? And then it's not going to be immutable? Here, it's one line, and everything's immutable. That is a new list that you get back. It is not that old list that's been mutated. It is a new one. So you're safe that way. One of the things that I wanted to look at, and I think that will be very interesting, yeah, so here's some, what you would think of as like normal Java code to go through and add 1 to that list. Well, so how many lines is this? And it only works on arrays of ints? You see this code in Java all over the place. In Scala, we have access to something like this, and it's generic. So that I can have map on a list of whatever type I feel like coming up with. I don't have to rewrite it as this 7 or 8 lines every time and have it mutate, which is, to my mind, really, really nice. All right. So I think if we're going to get a flavor for what the language looks like, looking at how map is implemented is going to be a good way of understanding both the syntax as well as the capabilities of the language, and understanding like where we were falling down before in sort of attaining pure functional goodness. So if we were to implement map in a generic way, I actually wrote up like 7 or 8 different ways of implementing map as sort of a, not a free function, but as free a function as you can get in Scala or on the JVM. And so this first way just goes through and it uses a for loop underneath in more or less the standard Java-ish, Scala-ish way. In that this is, in some sense, equivalent to a for each in Java. So we have that in the Java ecosystem. It's going to yield an iterator. We go through each of the elements. We do stuff, we mutate. What this code is going to do is it's going to declare a new list, iterate through the existing list up here, append to this new list, so you can see where it's declared as a var, and then return this new list. Okay, so that's not so bad. It's fully generic. It's taking our function up here. We can actually implement this a slightly different way. So what if instead of looping through each of the individual elements, we take a more functional approach of looking at a list and saying, well, list as a data structure really is a series of con cells with an empty cell at the end. Scala allows us, because of how list is constructed, as well as its language primitives, to say, yes, we can do this. So we can actually do sort of a recursive destructuring on list to implement map. And so we take our list, we do some pattern matching on it. This is, I guess, our first look at Scala's pattern matching notations. So it's similar to, I don't know, Rust, I think, is probably the one it's most similar to right now. Although I think Rust might be based on this at this point. Here's the expression that we're matching. Here's the match keyword to say, hey, we're going to do something with it. Here's the partial function. This is a way of defining the various cases of that partial function. Now, there's some magic that happens here, but because these are the way that they are, they're basically lowercase names, they're going to be variables that we can then use over here. So Scala has a way of distinguishing. Basically, uppercase names are going to be things like classes, and lowercase names are going to be things like variables. And so we know that this is going to be the head and tail of the list because the cons operator allows us to do pattern matching. Now, none of this is actually built into the language, which I think is really cool. This is, again, that syntactic elegance of pattern matching is implemented through a method called unapply. And unapply takes that value and destructures it itself. And then all of this is rewritten by the compiler at compile time into basically a series of branching if statements. So it's actually really quite fast, which I think is really cool. So what this is going to say is that if list has a head and tail, which if it doesn't, then it will match on this last one. Well, if it does, let's evaluate f on the head of the list, and then cons on that tail. So we're just going to recurse on ourselves. And then when we hit the end of that list, we'll just cons on nil.
So
And
should there be a case H?
No.
So what about a list of a single element?
T will be just empty.
Yeah, T is
It'll
nil.
be nil.
Got it. Very cool. Okay.
Yep. Which is really quite handy.
It is. That's cool.
Okay. So we can sort of do the same thing up here. And this, in a lot of ways, this pattern matching will just de-sugar into this so that they're really equivalent. The nice thing about it is that if we take our if loop and go one step further, we can actually write a tail recursive call that will not blow up our stack no matter how large the list is. Because I think the default recursion depth is something like 65,000. It's a lot, but it's not infinite. Whereas this, your list can be rather large. But you can see how the annotation, it's not magic that the Scala compiler does. Well, I mean, it is magic that the Scala compiler does. It's something that you have to opt into at compile time. So you have to have written your code so that it can be tail recursively optimized.
Doesn't it try to do a tail recursive optimization?
It does.
And like all that annotation does is make it compile safe.
It might, but small changes, as I found out, can break tail recursion. And so you really, I mean, if that's what you're going for, you really want to have that annotation.
Right.
So,
If you're doing recursive, you probably want to have the tail recursive on there.
Yeah, if you're using IntelliJ, it actually does the analysis for you. And so I used to always use the @tailrec notation, but since IntelliJ does the check and the compiler does attempt to do it, I stopped using it. It stopped. I mean, it just.
If you refactor.
Yeah, but the compiler is not always correct.
Good point. I have none of that, Jacob. Thank you.
what was that?
As if you refactor it and you don't have the annotation there. And you
Then,
know,
and you don't happen to look at the code and it's been refactored, you can't see that it's now saying it's no longer a tail
Oh,
recursive. Yeah, that was a good one. Yeah.
Okay, so here's our for comprehension, which again is not the same as the for loop that we had up at the beginning, because this, remember, is going through and appending to a list. This for comprehension is going through and automatically instantiating a new list and yielding the individually mapped members into that list. So it's actually very different code. It looks the same from the Scala side, and it can be tricky to see this sometimes, but it really is different code. It's really these last two that sort of draw our eyes away from just how different Scala is in the way that it thinks about functions like map and fold and reduce and collect and all the other ones that we use to work with on collections. So, yeah.
So does the return type of map for comprehension differ from, say, any of the other return types because it's like a flat map, it's like returning a list, or?
So no, the type inference algorithm will see that the monad wrapper of this first type, or this first binding up here, is list. And therefore it knows that whatever comes out of this has to be a list of whatever. So it knows it's going to be a list of A. So it's going to have to be a list of whatever that block yields, so a list of B.
Oh, okay. So the statement itself is being evaluated strictly then, but it's just that generator that's a little lazy. Like you've got to actually call it for. Never mind. I got it.
Yeah, I mean, flat map, it's going to be push. It's not going to be pull.
Right.
So the collection is actually going to be pushing as long as it has elements, it would be pushing it through that computation.
Yeah, C# yield is a bit different. I'm just getting.
Yeah. I don't know anything about C# yield. I think that's more of a continuation, like push it onto the stack trace or something. Or not push it onto the stack.
If you use streams, it's closer to that behavior where it waits to do the evaluation until you basically say, give me an element from this. Like you're on take 5 somewhere. But,
Oh, yeah. Okay, so like I was saying, the explicit method and the method concise really show just how different Scala is from other languages. So languages like F# and Haskell, you have lots of free functions. You just don't, they aren't owned by any particular scope. I think they can be, but I don't think it's required. In Scala, most of the way that people interact with methods like map and collect and all these kinds of things are as methods, not as functions, but as methods on collections, which introduces a lot of very interesting problems because, for example, everybody thinks that the signature of map should be something like that. But if you actually go look at the signature of map on list or sequence or something like that, you're going to see all kinds of other magic and get very confused because of the additional lifting that Scala does to make things like, well, I can have a list of tuples and basically just promote that into a map. Because as we saw in our map constructor, well, it takes a list of tuples and then it declares a map, right? Well, if I have a traversable, if I have a sequence of tuples, why can't I just always put that into a map? Well, turns out you can. So because you don't necessarily always want the out type to be the same as your in type, we use type classes in order to, this is where can build from and other things come from, to make it easier for us, but it also makes it harder for folks who come from a functional programming background because they see our type signatures and go, oh God, what the hell is going on? Well, that's what's going on. But this is like, this stuff right here really is probably 90 to 95% of what functional programming is in Scala.
Yeah.
Is doing functions over collections. That really is most of it. So, all right, what time is it? 8:10. So we'll see how many more modules we get through. Oh yeah, the Scala record is fun. No, not copy. There we go. Well, let's see. So this defines a function called head. Let me do this so everybody can see it. Head returns in a generic way the first element of a sequence. And I forget why I did that. Oh yeah, so that we can look. Oh, and that's why it has to be the can't be eminent. The reason I wanted to bring this up is that this is going to do something very different for us in Scala than it will for somebody in Haskell. So what is the type really of that function? I mean, if I look at the type signature up here, it's just genericized over sequence, right? It's a sequence of any types. And so that's, if I'm thinking about it as a Java programmer or a Scala programmer, it's just going to be a sequence of any type. If I actually go and ask the compiler what it is, it's a sequence of nothing to nothing. It's really kind of disturbing because if you're coming from a Haskell background, it's going to be like an A prime. So it should be a sequence of A prime to A prime, right? So what the hell just happened? Well, part of this is inference, and part of this is the fact that we have type erasure going on. And so we don't really have these type variables in our signatures the first thing that Scala goes and does is it eliminates all type variables. It gets rid of them, and it basically drives them down to the bottom type. And so, I don't know if this is illustrative to anybody, but if you see Scala signatures and you wonder why they don't behave like you would expect a Haskell signature to, well, this is part of the reason why, because they can't. We just don't have that machinery. I don't know if that's a limitation of the compiler. I think we could probably have it in place, but then you end up with interesting issues like, can I do partial evaluation? What if I have A prime and B prime? Things like that. So
You can carry around some level of